still on series. This is a bit. Hearing me right?
Yes,
Harriet?
sir.
Okay. So how were the exams?
They're okay.
A plus.
Not sure, but they're okay.
Alright, so method of differences is used to find the sum of a series whose general term can be written as the difference of terms. So if we can write a series as UR is equal to one function where we have R plus 1 minus a function of R, then we can do the summation as follows. So if we can write it in this form, then the summation will look something like this. So the sum from R is equal to 1 all the way up to N UR, and that's equal to the sum from N R is equal to 1 for the function. So basically both of these functions, R plus 1 minus function of R. So we'll see how this comes into play in a bit. But this is just a general reference to what we have going on here. And this particular topic, it sometimes links to partial fractions. So you might have to use some partial fraction to separate some terms given. All right, so let's see. That's a partial fraction. Let me get an example where we won't be linking to partial fractions just yet. All right, let's just do it. I believe most of these will give us partial fractions anyway. So what they would want you to do is basically prove something. Show that R plus 1 is equal to 1 over R minus 1 over R plus 1. And we'll have to use method of differences to show this. So they want us to show that that is equal to that, and then follow-up question, hence find the sum of this thing here. All right, so as stated, in order for us to do this, we would need to separate this thing here into partial fractions. So we will have, it's a different color, 1 over R plus 1, and that's equal to A over R plus B over R plus 1. Following?
Yes, sir.
So now you know we do our cross multiplication to get rid of the denominators. So we're going to multiply both sides by r open bracket r plus 1. So we're going to have 1 is equal to a times r plus 1 plus b times r. So this is what we have so far. And we need to eliminate, well, we need to solve for these variables. So we could say let r be equal to 0 to get rid of the b. So when r is 0, we have 1 is equal to a times 1 plus b times 0. So a is equal to 1. So a is equal to 1. We can substitute that to find what b is. So when a is equal to 1, we have, or let's use r as negative 1, sorry. To get rid of the a term here. So when r is equal to negative 1, we would have 1 is equal to a times 0 plus b times negative 1. So that's negative b. So b is equal to negative 1. So, oh yeah, we're basically done. Because they said we should show that. So for this part, we're just actually proving that this left-hand side is equal to this. So a would be 1. So let's replace it with 1 here. And the negative 1 as b. So therefore, we would have proven that that is true. So r plus 1 is equal to 1 over r minus 1 over r plus 1. So we would have proven that. Then they said, hence, so this part, need to find the sum of that. And what we just found is what we'll have to use to prove it. So let me get on a new page. So this is the hence. They want us to find the sum from n, where r is equal to 1, well, leading up to n, 1 over r plus 1. Alright, so we just proved that this is equal to the same thing as, so if we replace this piece with the partial fractions we just proved, that's going to be 1 over r minus 1 over r plus 1. So this is what we need to find the sum of. So now what will happen is that if we expanded this series, so let's say we're expanding and we're starting at 1. So when r is equal to 1, I want to see if we notice any pattern here. So expanding, let's see, expanding. So we're expanding here. So we will have, so when we use r as 1, so what I'm going to do is just going to combine a few of them to see if we can identify a pattern. So when r is equal to 1, we're going to get 1 over 1, right? Minus 1 over 2. And remember, series, we're basically summing all of this up to n. We don't know what n is, but we're just going to do a few to see if we notice anything. When r is equal to 2, that's 1 over 2 minus 1 over 3. When r is equal to 3, that's 1 over 3 minus 1 over 4. And then we continue until we get to plus, when, well, we aren't quite at where r is equal to n as yet. We have a few terms before it, even though those terms are going to cancel out each other, because if we notice here, we have 1. This 1 isn't cancelled out by anything. However, this negative a half is cancelled by the positive a half. Can you see that?
Yes, sir.
This negative a third is cancelled by the positive a third, negative quarter, positive quarter. So this will happen all the way up till we get to the n term. So the only thing that we really need right now is what will happen when r is equal to n. So we will get 1 over n minus 1 over n plus 1. That's all the way up to our nth term. And then as we said, everything will cancel. So those will cancel out each other, and this term will be cancelled by the term that would have been in the bracket before. So the term before n would be n minus 1, right?
Yes, sir.
So if that term, if we were supposed to substitute it here, we would get 1 over n minus 1 minus 1 over n. And you realize that this is a negative, so it will cancel this right here. And then the pattern will just continue all the way until everything in between cancels out. So all that we're left with is the 1 here at the start and the minus 1 over n plus 1 at the end. So everything will cancel. So just remember that. When working with methods of differences, everything is going to cancel except the first and the last term. Alright, so what we're left with now is the sum from n and that's going to be equal to 1 minus 1 over n plus 1. And this would be your answer. So you just leave it like this. Good?
Yes, sir.
Alright, let's try another one. So this one says, I think I should do it on another page. Show that r plus 1 all squared minus r squared is equal to 2r plus 1. Then it says, hence, find, so part A wants us to find the sum r is equal to 1 part B wants us to find the sum r is equal to 1 all the way up to 20. Alright, so let's see how we can apply a method of differences to this one. Now this one is a little bit different, and so I guess in the previous part I shouldn't have said that we only keep the first term and the last term, because it all depends on what we notice being cancelled out when we are writing out the terms, because it doesn't necessarily have to be the first term that's cancelled out. So we just have to pay attention to that. So it's not the first nor the last only or always. So once you're cancelling out, you will see what is being cancelled out. So, so they said that they need us to show that this is equal to 2r plus 1. So all we'd have to do is just expand this, simplify. So r plus 1 all squared minus r squared. So expanding this is going to give us r squared minus 2r plus 1 minus r squared. So r squared cancels, so this is just 2r plus 1, which is true. So that means this which they asked us to show is indeed true. So now for the first part, we need to find the sum from r is equal to 1 to n of 2r plus 1. And this would be the same thing as the sum r is equal to 1 for r plus 1 all squared minus r squared. So this is what they want us to actually find. So now, once again, we need to substitute some values to see what happens. So when r is equal to 1, we're going to have, this is 2 squared, because 1 plus 1 squared minus 1 squared plus, when r is equal to 2, that's 3 squared minus 2 squared plus, when r is equal to 3, 4 squared minus 3 squared plus, all the way up to the, when r is equal to n, we're going to have n plus 1 all squared minus n squared. So what do you notice here? What's canceling out what?
So I said the 2 squared and the other 2 squared and the 3 squared and the other 3 squared.
So that means 4 squared. So once you get something to cancel out in the first bracket and it leaves a term, you know that this term will be in your final answer. So this minus 1 squared is going to be in our final answer. And then for the last bracket, we need to see which one of these are cancelled out. So that means we would need to find the term before this. And we said that the term before n, we get to n is what?
N minus 1.
So n minus 1 would be our term. So let's see what happens when we're working with n minus 1. So this would be, so we're substituting the r with, well, the r over here with n minus 1. So this is going to give us n minus 1 plus 1 all squared minus n minus 1 all squared. So this is just n squared minus n minus 1 all squared. So if we look closely, we realize that we have a negative n here, well, negative n squared, and we have a positive n squared here. So this is the term before. So that means that will cancel in the last bracket. And then we don't need to go any further, because if this cancels both of the terms, and then this one is going to cancel the positive n minus 1 squared that would be in the previous bracket. So that means this term here is safe. So in our final answer, this is what we're going to use. So to combine our answer now, so we have this minus 1 squared, we have n plus 1 all squared. So to combine our answer, we're going to have the sum r is equal to 1 for n, and we're basically giving them back what they wanted, 2r plus 1 this is going to be equal to n plus 1 all squared minus 1. We can expand. So this is just n squared plus, and the reason why we're expanding and simplifying is because of this piece. We need to evaluate this. So part B said that they want us to find the sum up to 20. So the sum from r is equal to 1 up to 20 for 2r plus 1. And remember, 2r plus 1 is the same thing as this, n squared plus 2n. So what will happen now is that we can simply replace this n with 20. So this is just 20 squared plus 2 times 20. So that's 400 plus 40, 440. Following? So there are those that would I'm not sure how long you got kicked off. However, um, we used the n squared plus 2n here because, well, we use it down here because we, after evaluating using method of differences, we noticed that 2r plus 1 is the same thing as n squared plus 2n, and they want us to find the sum up to 20. So all we're doing is taking this function here, or this sum series rather, and substituting 20, and then we simplify, get our answer. So there are cases where you'd have to use partial fractions to separate the term like this. So you'd want it to have two different terms. So there are cases where you'd have to use partial fractions, and some where you just expand, simplify, and get your result. So let's see another one. I want to give you one to try. Let me do another one and then I'll give you one to try. So I'll go through one more quickly. Which one should I do? Alright, so this is a crazy one. So given that 3r, open bracket, r plus 1 is equal to all of this over here. This is not an equal sign, this is a minus sign. We should show that the sum All right. So they want us to prove this. So we're going to have to use the right hand side to do something. All right, so show that this is equal to this. So since 3r is equal to all of this, so I guess they would have multiplied both sides by 3. So what I was saying is that, seeing that, so this 1/3 is just here to throw us off. But what we could actually do is multiply both sides by 3 to get rid of this. And then once we do that, on the right hand side, we realize that this is the same thing as r is equal to 1, 3r, r plus 1, right? On the right hand side.
Yes, sir.
And see that we already know what 3r times r plus 1 is, we can just replace that, well, all of this over here with r. That would be equal to the sum r equal 1 n r plus 1 r plus 2 minus r minus 1 r plus 1. So we have it like this. So now it's just time to test, and both of these are separated by a minus sign, so that's a good way to know that we can use that to test by expanding or substituting values to see if anything cancels. So when r is equal to 1, over here we would have, so the first thing we would have in the bracket is 1 times 2 times 3 minus, okay, this is 0, so that's just 0 times 1 times 2. That's our first bracket, plus, when r is equal to 2, that's 2 times 3 times 4 minus 1 times 2 times 3. And if this continues, let's do the nth term. When r is equal to n, we will have n times n plus 1 times n plus 2 minus n minus 1 . Alright, so what we noticed so far is that, let's see, 1 times 2 times 3 cancels. So 1 times 2 times 3 cancel. We would have needed, well, we wouldn't need it necessarily, because everything except something in the first bracket will cancel out. So this is the only thing that isn't cancelled out. That's just a 0, so it's not even necessary. Now in the last bracket, we have all of this. So we would need the term before this one to see what actually cancels out. But based on the pattern that I'm seeing here, this will cancel. But if you aren't too confident, you could test it. So the term before the nth term is n minus 1. So we can replace all these r's here with n minus 1. So that will give us n minus 1, sorry, n minus 1 times n minus 1 plus 1 times n minus 1 plus 2 minus n minus 1 minus 1 n minus 1 plus 1. So that's going to give us n minus 1 times n times n plus 1 minus n minus 2 n minus 1 n. So you realize that this term here, use a different color to highlight it. This term here would have been cancelled out by that one, right? So all that we're left with is this one right here. So everything else would cancel, leaving that one. So that would cancel that, and this would cancel the term before that one. So we're left with n plus 1, n plus 2. So next page. So we could say that 3 times the sum all the way up to n r equal 1 is equal to n plus 1 n plus 2. And then what did they say again? We're actually proving this. So to prove it, we just divide both sides by 3. So just divide by 3 to actually prove what they want. So the sum r is equal to 1 is indeed equal to 1/3 n plus 1 n plus 2. Good.
Not really.
Where are you? Where did I lose you?
The previous page, on the bottom.
Down here?
Yes, sir.
So this is where we were using the n minus 1 term, because this part here is the nth term. So in order for us to prove that, because remember we said that something from the first bracket is going to remain, something from the last bracket is going to remain as well. So what we had to do was, so when we realized that this is what's going to remain from the first bracket, we're good, everything else will cancel out. But from the last bracket, we need to know which one of these will remain. So we had to find the term before the nth term. So that would be our n minus 1 term. So what happened is that we substitute, so wherever we had r, we substituted n minus 1. So look at this. So in all of this is where we're going to substitute n minus 1. So this is the r, we substitute n minus 1. R plus 1, we substitute n minus 1 plus 1. R plus 2, n minus 1 plus 2. Minus n minus 1. So in where's the n minus 1? We're just replacing the r. N minus 1 replaces the r. N minus 1 replaces the r. And then in this second line is where we simplify. N minus 1 remains. The minus 1 and plus 1 will cancel. So that's just n. This is going to give us a plus 1. Put back our minus sign. This is going to give us minus 2. Put back the n minus 1. Nothing cancels there. And over here, minus 1 cancels plus 1. So once we get this last line here, this is what will happen when we get to the n minus 1 term, all of this. And then we realize that this is up to the nth term, right?
Yes, sir.
So remember we said that something from the last bracket will remain. So we look at the previous bracket and realize that we have a positive n minus 1 and n plus 1. In the last bracket, we have a negative n minus 1 and n plus 1. So this will cancel with this one. And then this would have been cancelling with the previous bracket. So from the last bracket, this is what remains. Seen it now?
Yes, sir.
So you just have to replace the r value with n minus 1 or sometimes even n minus 2 to see exactly what is happening. So if we get to any more, we'll look at, I think, the other examples aren't like that. Let me see if I can find one to give you to try. So this is method of differences. So I'm not seeing any right now. So okay, try this one. So given that, so that's r bracket r plus 1 minus r minus 1 times r. Find the sum all the way up to n, r equals 1 for r. So try this one. finish?
No, sir.
So let me know if you need any assistance.
Yes, sir.
Alright, so we're given this. We need to find the sum of the r. So the usual case would be to prove that these are equal. So let's use the right hand side. So this is r squared plus r minus r squared plus r. So this is just 2r. And left hand side equal right hand side. So let's go. So they want us to find the sum up to n when r is equal to 1 for r. So if 2r is equal to this, to get r, would have to use half of whatever that is. So we'd have to use half, because that's the only way we're going to get back 2r if we multiply both sides by 2. So now we can evaluate this thing here by substituting some values. So when r is equal to 1, or let me just get back. So times 2 times 2. So you know that will be going with that. Alright, so on the right hand side here, when r is equal to 1, we're going to be getting 1 times 2 minus, that's 0, 0 times 1 plus, when r is equal to 2, that's 2 times 3 minus when r is equal to, well, I guess we don't need any other term there. Because we notice what's going to remain from the first bracket, this part here. This is going to cancel out next one. That's when r is equal to 3. Yeah, when r is equal to 3, that would cancel here. So when r is equal to n, or let's do the n minus 1 term. When r is equal to n minus 1, we're going to have n minus 1, n minus 1 plus 1 minus n minus 1 minus 1 n minus 1. So you see how we get this one? This is when the r is equal to n minus 1. So replace all these r's with n minus 1. So you're seeing that?
Yes, sir.
So now we'll look at when r is equal to n. So that's n plus 1 minus n minus 1 times n. So this will be our last term. And based on everything that we're seeing so far, this will cancel out this. That's the same 1 times 2, 1 times 2. This is going to cancel out by the next term. So in the last bracket, we need to see what will remain. So in the previous bracket, we have a n times n minus 1. This is negative. This is also negative. Over here we have n minus 1, that's positive. This is negative. Okay, so this will cancel out this one. And this will be cancelled out by the previous n minus 2 term. So this will be cancelled out by the previous bracket. So what's remaining here is our n times n plus 1, sorry. So this is all that's left. This 0, even though it remains 0 plus n times n plus is still n times n plus 1. So we don't even need to regard this 0 here. So all that's left is n times n plus 1. So that means on the right hand side over here, 2 r is equal to 1 is equal to n times n plus 1. And then remember, what they wanted us to find was this with just the r. So how do we get rid of this 2 here? How do we get rid of this 2 that is on the outside? Still with me?
Yes, sir.
So I was asking, how do we get rid of this 2? So this 2 is multiplying. So we look for the opposite operation. If it's multiplying, we're going to divide everything by 2. And once we do that, the sum when r is equal to 1 up to n, where this is going to be n plus 1 over 2. Does this look familiar to you? N times n plus 1 over 2.
Yes, sir.
So this is one of the general results. I realize that through all of this working out, we're able to prove back that this is equal to that. So that's how we apply methods of differences. And as I've stated, some of these you'll have to convert it to partial fractions to see what you'll be working with on the right hand side. So you must or you definitely have to convert it to partial fractions to get what you're working with on the right hand side. So you just need to practice a few more. Check through the past papers to see what exactly or how these questions occur on the exam. However, that's it for method of differences. So before we wrap up this chapter in the module, the last thing that we need to look at is convergence of a series. And there are a few ways in which we can actually test for convergence. So convergence. So seeing that Asha Mark isn't here, I think we'll just do the 2 hours. Next week we can try and get our 4 hours in. So convergence of a series. Right, so we know that a series is basically the sum of sequences. So sometimes it's represented as this Sn. It's basically saying the sum of sequences. So we have u1 plus all the way up to n. And then if the limit, so we are back to limit as n tends to infinity of a series is equal to that series, then we can say the series is convergent and the series converges to S. Or, yeah. So, what was I saying? So if the limit exists, is convergent, and if the limit does not exist, then it is divergent if it's infinity or does not exist. So it has to actually have a limit for us to say that it is convergent. It converges to that particular value. So if the limit as n tends to infinity, the series is equal to infinity or negative infinity or the limit does not exist, so 3 conditions for divergence. So these are the 3 conditions. If it is positive infinity, negative infinity does not exist, we can say that the series is divergent. And then for convergence, we have to have a particular limit for it to be convergent. All right, now let's look at how we actually, or how we're able to actually do this. So remember, one condition for convergence is that the limit must exist. For divergence, positive infinity, negative infinity, or even if the limit does not exist. Alright, so let's start with a simple one. So given that, when r is equal to 1, and we know that this is just n plus 1 over 2, we want to prove if this is convergent. Is this series convergent? Remember, we said that for it to be convergent, it must have a particular value as it approaches infinity. So let's say Sn. So Sn will represent our series, and this is equal to n plus 1 over 2. So we need to take the limit of this. So the limit of Sn, well, as n tends to infinity, for this would be equal to the limit as n tends to infinity for n plus 1 over 2. So looking at this would simply give us infinity, right? Because if we substitute, do a direct substitution, it's just infinity times infinity divided by 2, which is just infinity, right?
Yes, sir.
So that means since this is infinity, the series diverges. So it's not convergent. So since the limit as n approaches infinity for the series gives us infinity, we can simply say the series diverges. Alright, let's try another one to see if we can get one that actually converges. So let's say we're given the following. And we're told that this is equal to 3 over 4 minus a half, and then they said that is this series convergent. So before you even working this out, what would you say? Is it convergent? Is it divergent? What would you say? Not sure.
So I don't know what you asked.
I'm saying, is it convergent or divergent by just looking at it?
Not sure, sir. Probably Divergence. I don't know.
So remember limits when we're moving to infinity, and because what would happen now is that we would need to take the limit of all of this on the right hand side, and we'd have to separate them into individual parts. So the limit of 3/4, the limit of this thing here where n would be in the denominator, the limit of this thing here where n would be in the denominator. And then we said if we're taking the limit as n tends to infinity for 1 over n, this would give us a result of 0. Remember that from limits? So
No.
whenever we have the variable in the denominator tending to infinity, this result will always be 0. So just remember that. This is one of a very important limit that you'll encounter over and over in various topics. This one in particular. So just remember that. However, based on what they gave us in the question, we would need to find the limit as n tends to infinity of the series, and this would be, let me move this over a bit. Let's bring this down here. And this would simply be the limit n tends to infinity for this entire thing here, 3 over 4 minus a half 1 over n plus 1. So taking the limit of all of that. So I'd have to separate the limit using the sums and differences rule. So this is just the limit n tends to infinity 3 over 4 minus the limit as n tends to infinity. So distributing the half would get 1 over 2n plus the limit n tends to infinity. Distributing the half, well, it would be minus wouldn't even necessarily need to distribute the half, but yeah, let's just 1 over 2n plus 2. We wouldn't, all of this would still give us the same result. So the limit of a constant as it tends to infinity is just that constant, so this is just 3 over 4 minus, and then we said that the limit of this piece here, we're tending to infinity. So if we should do a direct substitution here, it would just be 2 times infinity. And remember, 1 over infinity is 0. So this is just 0, and the same thing here. 1 over infinity, 0. So this is just 3 over 4. And we said that if we take the limit to infinity and the result is, we actually get a result, then we can say that the series converges to this particular value. So therefore, the series converges to 3/4. So that's one way we can test for convergence, we actually have multiple ways. However, in your syllabus, you will be exposed to the integral test, um, for, well, just integral test and the limits, that's all. And then we have the divergence test, the Allenbert's ratio test, and that's it for convergence and divergence. Then next week we'll look at principles of mathematical induction with sequences and series. All right, so let's look at the integral test. I think I should give you one of these to try first. Let me look for a question. If I can find any, that is. Alright, that one is going to be too long. But that's a good question though. Those those will have to be. Alright, we'll just finish up with the notes part, and wherever we are after, we'll see what we can get done. Alright, so test for convergence of a series. So test for convergence of a series. So as stated, there are many ways we can test. However, on your syllabus, you won't need to know all of them or that many. So theorem, if, so this is a theorem. So you're saying that if we have a sequence here that converges, then the limit as n tends to infinity would be equal to 0. However, we can't say because the limit is equal to 0 then it converges. So it's not how would I say, commutative, where we can say if it goes that way then it must go the other way. But we'll see more of that as we go along. So as stated, we want to look at the integral test. Alright, so the integral test, so I'm going to give you the general notation for this. So if f of n is equal to all right, which one should I use? All right, let's use this one, un. So we're looking at continuous, positive, and decreasing and this is ranging from 1 to infinity. So this is in interval notation. This is saying that we're going from 1, where 1 is inclusive, to infinity, where that is not inclusive. Then what we have now is two conditions. So if we're integrating from 1 to infinity of this particular function with respect to x, or if the function converges, then n equal 1 to infinity converges. And diverges is just, if this diverges, then the sum of that series would diverge. So it's the same condition, however, one diverges, one converges. Alright, so we want to look at how this is actually applied using the integral test. So show that Alright, so in a given question like this, what we have to do is to change this as a function of x. So we can say let f of x be equal to 1 over x. So basically, so for this, we're basically changing out the n with x. So this is our function, and we need to show that integrating this from 1 to infinity of this particular function with respect to x. So this would be the integral from 1 to infinity of 1 over x, because we changed our n to x, and integrating this would just be infinity. So you've seen that, right?
Yes, sir.
So if we integrate this, we'll get back infinity. Because all we're doing is substituting after we take the integral. Yeah, that's just infinity. And we could actually use the areas of rectangles to prove the sum, but we don't need to go that far. We can just say that this is equal to, so this on the left hand side or above would be equal to this. And then once it is equal to infinity, we can say that it diverges. And they would refer to this as a harmonic series. However, that's not quite important right now, but they would refer to it as a harmonic series. So looking at this, we would say that it diverges. All right, so let's look at one that actually converges. So determine if all right, so we need to let, so that's the first thing, let f of x be equal to whatever we're given to find the sum of. So let f of x, oh, and we're replacing the n with x. So that was going to be x e to the negative x squared. So that means we need to take the integral of this from 0 to infinity. So whatever the initial value there was, that's what we're going to take the limit from. Fx dx, that's equal to the integral from 0 x dx. Alright, so integrating this, alright, so and then next we have the divergence test. So I have the divergence test and the Allenbert's ratio test. So if So if the limit of this is not equal to 0, then it diverges. So it's an example, is so we need to take the limit as n tends to infinity of n over n plus 1. So separating this, this can be separated using partial fractions. This is what we did earlier. Let's see. The first thing that we did, yeah, it was this. So this expansion, or this, is what we have now. So in a case where we're given one of these, we can separate it. Method of differences. So this part here will be separated as the limit as n approaches infinity of 1 minus 1 over n plus 1. And we know that anything with n in the denominator going to infinity, that's going to be 0. So this result is just 1. And based on the rule, if the limit is not equal to 0, then it will diverge. So we can simply say that since the limit as n tends to infinity for n over n plus 1 is not equal to 0, the series diverges. So we have that down. Alright, so the last thing on the convergence and divergence for now is the Allenbert's ratio test. So the Allenbert's ratio test. Alright, so the Allenbert's ratio test states that for a positive, or a series of positive terms of the form, so what we're looking for, so states for a series of positive n equals 0. So these are the conditions. So if the limit as n approaches infinity so plus 1 over u n. So if the limit of this is less than 1, then the series converges. If the limit as n approaches infinity if it is greater than 1, then the series diverges. And lastly, if the limit as n approaches infinity is equal to 1, we need further testing. So that could be the integral test. And as I've stated, there are a few other tests. We need to test further. All right, so let's do an example here. Determine going up to infinity so determine whether this series converges. So what we're doing now is, so based on the ratio test, we need to have two different series working with. So we need to have a series where we get un plus 1 and un would be our original series. Let's look at it. So this series given to us, we would represent it as un. So we would say let un be equal to 2 to the n minus 1 over 3 to the n. Then we can say let u n plus 1. So what's happening is that we're replacing the n with n plus 1. So that's going to be 2 n plus 1 minus 1 over 3 n plus 1. So up here it's just 2n over 3n plus 1. Following?
Yes, sir.
So this is our original series given, and this is the one that we would have to formulate as the n, where we replace n with n plus 1. So now based on the ratio test, we need to have them over each other. So we need to say that u n plus 1 over u n. So that's going to give us 2 to the n over 3 n plus 1 over, so this is our un plus 1 term, and this is divided by 2 to the n minus 1 over 3n. So we just divide them. So now we know that dividing two fractions, we keep change flip. This is going to give us 2 to the n over 3 to the n plus 1 times, or let me not skip that step, divided by 2 to the n minus 1 over 3 to the n. So now that's going to give us 2 to the n over 3 to the n plus 1 times, so keep change flip, that's 3 to the n over 2 to the n minus 1. Alright, so simplifying this a bit further, we know that, alright, let's see what we can do from here. So in the denominator, alright, let me bring this on the next page. I'm going to need a little bit of space. Alright, so in our new, I'm going to rewrite it. So numerator is just 2 to the n. Denominator now is 3 to the n times 3, right? We're just separating this. So that is being multiplied by 3 to the n over 2 to the n times a half. Let me know if you're seeing that.
No, sir.
So this 3 to the n plus 1. So remember, laws of indices, if we have same base, we can add the exponents. So these will be the same base, we're adding the exponents. You're seeing that now?
Yes, sir, I see that one.
And then same would go for the 2 to the n minus 1. Same base, the exponent for here would be n, the exponent for here would be negative 1. And then we know when we have the negative exponent, we can flip it. So it's just 1 over, seeing it now?
Yes, sir.
So that's what we have there. So now this will cancel, 2 to the n will cancel, 3 to the n will cancel, and all we're left with is, so in the numerator is just 1 over 3 times a half. So this will give us 1 over 3 times 2 over 1. So that's just 2 over 3. And that would be your answer. So 2 over 3 is equal to 0.666. So this is less than 1. So this is less than 1. So that means the series converges. So we're good with that?
Yes, sir.
So what I'm going to do is look through the past paper, past papers, and see if I can identify some of these questions and how they apply them. So next week we will just start off with some of them and then we'll go into mathematical induction